We will take up one more problem on simply supported beam, the problem number 16. A simply supported beam is loaded as shown in the figure. Draw the SFD and BMD, also find the position and the amount of maximum bending moment. So here we have a simply supported beam of span of 6 meters, wherein AB, you have 1000 Newton meter UDL, and also you have a 1000 Newton meter on the left hand to 2000 Newton per meter at the right hand B. So you have the combination of both uniformly distributed load and also the uniformly variable load kept one above the other. So we need to find out what is the support reaction. Let RAV and RBV be the support reactions at the point A and B. So the load intensity may be assumed to be split up into one is UDL of 1000 Newton per meter over the entire span, and also uniformly variable load from 0 at A and to 1000 Newton per meter at B. So taking the moments about the point A, so first we are going to take RBV into 6 will be equal to, then 1000 into 6 into 6 by 2. That is, first we are going to consider the uniformly distributed load and then uniformly variable load, taking the moments about the point A. So half into area of the triangle, half into 6 into 1000, half into 6 into 1000, and the distance of center of gravity from the smaller end, which will going to be 2 by 3 into 6. So 2 by 3 into 6. On simplification, RBV will going to get 5000 Newton. Then also we know the sum of the vertical reaction acting upwards will be equal to sum of the downward reaction. So RAV plus RBV will be equal to 1000 into 6 plus half into 1000 into 6 again. So RAV will be equal to 9000 minus 5000 because RBV is 5000. Therefore, you will going to get it as 4000 Newton. So you will going to get the reactions at A as RAV, which is 4000 Newton, and reactions at B, which is RBV, is equal to 5000 Newton. Now we will going to consider the section on the uniformly variable load. Consider the section XX at a distance of X meters or from A when you are considering the section. So what we are trying to do? We are trying to do on this section, that is on this uniformly variable load, we are considering any section at a distance of X meters from A. So that is the reason why I am writing only this particular diagram, because UDL is uniformly distributed. So once you are considering that, so from the similar triangular principle, what you have, we have the two triangles. One is ABC and the other one is ADE. So what is that? BC by AB will be equal to DE by AE. So BC by AB will be equal to DE by AB AE. So what is BC? BC is nothing but 1000 Newton per meter divided by AB is 6 meters will be equal to, we don't know what is the height, that is the one which I need to find out. So that DE by X. So what will going to be the height of this triangle? The height of this triangle ADE will be equal to 1000 by 6 into X. So that is what we have written, the consider the section at a distance XX. So that will be 1000 into X by 6. Now once you get that, you will going to incorporate that here on both UDL and also on the variable load. So we are considering the section now. Considering the SF at section XX, at this section, what will going to be the shear force? Shear force will be equal to 4000 minus 1000 into X minus area of the triangle. So area of the triangle is minus half into height is of this section from here to here. It will be 1000 into X by 6. That is the height into base is the length, which is going to be X. So on simplification, you will going to get that is equal to 4000 minus 1000 into X minus 250 by 3 into X square. So when the value of X is equal to 0, what happens? Shear force at the point A will be equal to 4000. You will going to get directly plus 4000 Newton. So that is what we get at this point X 4000 Newton. So what will going to be the bending moment? So the bending moment at the section XX will be equal to 4000 into X minus 1000 into X by 2 minus half into area of the triangle. Area of the triangle is x into 1000 into x by 6 into the distance of center of gravity from the bigger end, which will be x by 3. So it will going to be x by 3. So that means 4000 into x, that is load into this distance, minus the entire uniformly variable load, that is 1000 Newton per meter. So minus 1000 into x by 2, minus half into height is 1000 into x by 6, that is from here to here, into x, that is the base area of the triangle, into the distance of center of gravity from the bigger end, which is x by 3, because we are considering the bending moment at this section xx. So now, on simplification, you will going to get it as 4000x minus 500 into x square minus 250 into x cube by 9. So when the value of x is equal to 0, you will going to get that point as 0. So BM at the point A will become 0. Then we are considering again the section. SF at section XX will be equal to, you are getting that 4000 minus 10,000 into x minus 250 by 3 into x square. Suppose when you are considering the value of x is equal to 6, what happens? When the value of x is equal to x, substitute SF at the point B now. SF at the point B will be equal to plus 4000 minus 1000 into 6 minus 250 by 3 into x square, that is 6 square. Substitute the value of x as 6, so it becomes minus 5000 Newton. So that means from here to here, you will going to get a parabolic curve, because the power of x here is 2. So therefore, in shear force diagram, you will going to get that point as the parabolic curve. So SF varies according to the equation of parabola. What will going to be the bending moment at the section XX? Obviously, it will going to remain the same. That is because when you are considering the x, so it will going to remain the same as this. That is the old one. That is 4000 into x minus 500 into x square minus 250 into x cube by 9. Now, when the value of x is equal to 6 now, what happens? BM at B. So when you're multiplying 4000 into 6 minus 500 into 6 square minus 250 into 6 cube by 9. So on simplification or on calculation, the value of bending moment will going to become 0 there. So it started from 0, it ends at 0. But we don't know what exactly the maximum bending moment which we need to find out. Why? Because the shear force changes its sign from positive to negative at this point, which is C. At that point, you will going to get what will going to be the bending moment. So since what I need to find out first is at what distance the C changes its sign from positive to negative. So if you find out that at that particular point, what will going to be the maximum bending moment we can apply. So to do that, so you're going to get x. So maximum bending moment occurs at a point where SF changes its sign from positive to negative. Let C be the point at a distance of x meters from A where SF changes its sign. So since it is the section XX, so at the point C, SF will be equal to 0 because the value is changing its sign from positive to negative. So the shear force value will be 0 at that point. So what is SF at C? SF at C will be equal to plus 4000 minus 1000 into x minus half into 1000 into x by 6 into x. Because wherever you take the section, the value of that 1000 into x by 6 will going to remain the same, because you don't have any other load which is coming on this. So that is the reason why the height will going to remain as 1000 by 6 into x. So now, so that will be equal to 4000 minus 1000 into x minus 250 into x square by 3. So on simplification, that means when you take the LCM, 12,000 minus 3000 into x minus 250 x square is equal to 0. So on further simplification, you will going to get it as 0 is equal to 48 minus 12 into x minus x square. So when you take out the multiplying throughout by negative sign, you are going to get it as x square plus 12x minus 48 will be equal to 0. So this is the equation of the quadratic equation. So we will going to apply the roots as minus b plus or minus root of b square minus 4ac by 2a. So minus b becomes, it becomes minus 12, a is 1 and c is 48. So minus 48. So substitute that minus 12 plus or minus root of 12 square plus 4 into 1 into 48 by 2 into 1. So on simplification, the value of x will going to be 3.165 meters from A. So now we are applying that the shear force will going to change its sign at a distance of 3.165 meters from A. So what will going to be the maximum bending moment? So the maximum bending moment at the point C will be equal to 4000 into x. That value of x is 3.165. You multiply that minus 500 into x by 2. So that means you will going to get, on simplification, you will going to get minus 500 into 3.165 square. That is, we have the bending moment equation in terms of x. You substitute that in this particular expression. So what I am trying to do here, so I am taking this expression wherein the bending moment, which will going to be at this expression, what we are talking about, 4000 into x minus 500 into x square minus 250 into x cubed by 9. So considering this expression, substitute the value of x as 3.165 on this expression. That is what we are trying to do. So here, so 4000 into 3.165 minus 500 into x square, that is 3.165 the whole square, minus 250 into x cubed by 9. So that will be x value is 3.165 cubed by 9. So the value will going to be 6770.7 Newton meter. So when you plot that, you will going to get the maximum bending moment is at this point 6770.7 kilonewton meter. So here, joining from this point to this point, again is coming to this, will going to be a cubic bar. So even though you have UDL, on UDL you have uniformly variable load. Therefore, the power of x is more for the UVL. So naturally, the more power, whichever the more power you have, that is the one which should be represented. So therefore, since it is a cubic curve, so cubic value, that is x cube. So therefore, you could going to join the line points by means of a cubic bar in the bending moment diagram. So here, that is because the uniformly variable load is applied for the entire span. So that is the reason why you are getting for the entire span, it will going to be a cubic curve in bending moment diagram, and in the shear force diagram, it will going to be a parabolic curve. So this is, so the bending moment varies according to the cubic law. So this is how you will be able to analyze and plot both the shear force and the bending moment diagram, and this will going to be the final solution. Thank you.